Hello everyone. So we have been talking about or discussing about monotectic phase diagrams, and in the last class I show you that the difference between the other phase diagrams and monotectic phase diagram lies in the fact that there is a concept called liquid phase immiscibility, and the liquid phase immiscibility is what dictates the microstructure formation in monotectic phase diagrams. So, before I really talk about the phase diagram, I would like to again show you some of the slides I showed in the last class on liquid phase immiscibility. In our childhood we have done experiments like putting kerosene and water in a beaker. That is what is shown here. You see that if I put kerosene in water, kerosene is lighter than water, and therefore kerosene will float on water. So, but the fact is that kerosene and water does not mix with each other. That is the most important aspect of discussion today, that these two liquids are immiscible with each other. That means they do not like each other at all, that is why they remain separate. Similarly, this is, if we just take a mustard oil in your kitchen and put it in water, and you will see that mustard oil will float on water. That is because mustard oil is also lighter than water. So, the fact that these two liquids they remain separate, this is water and there is a boundary between mustard oil and water, clearly tells us that at room temperature these two liquids are immiscible. They do not like each other, so they want to remain separate layers. Now, one can also do experiments which I was discussing in last class. I can take a syrup like any cough syrup and put in a glass and then water and a vial together, then all these three liquids will remain separate, they will not mix each other. Like you see, this is syrup, this is water, and this is the vial, because syrup is heavier than water, so it will settle at the bottom. So, now question is this is what dictates all the microstructural formation and also the phase diagram in monotectic system. So, you have to keep in mind this aspect, please do not forget. You can also have a situation in which if you add water and oil and stir nicely, then you will, with a surfactant or without surfactant also it will happen. Surfactant is nothing but which forms allowed to form the bubbles, like so it will form bubble or water droplets, rather oil droplets in water. These are oil droplets in water and well nicely mixed in the way that they remain separate. Okay. They are each droplets of oil in water, and that is known as emulsion. Emulsion is very common thing in monotectic phase diagrams, which we will discuss today itself, and this is also very common in the monotectic phase diagrams. So, now in metals or many of these phase diagrams which we discuss, we cannot see these things exactly in the liquid state, because metals in the liquid state are opaque to light and also very difficult to handle high temperature. So, what you see is a solidified state. Suppose lead and aluminium, as I shown in the phase diagram in the last class, lead and aluminium they do not mix each other in solid state liquid state either. So, because of this immiscibility both in liquid and solid state, what will happen, lead will come out as droplets, as you see here, these are the lead droplets in aluminium matrix. So, as you understand, lead is a very soft phase, okay, has a very low melting temperature as compared to aluminium. So, therefore, this kind of material is a good material for lubricating or friction anti-friction applications, because lead being a soft phase will act as a lubricating film on the surface of the mating surface in which the wear will happen, okay, which will impart the wear on this material. So, that is why this copper lead, aluminum lead, this alloy system become very important. They are all monotectic alloy forming systems. And then I can also show you another microstructure which is taken from my own work. You can see here, these are the bismuth droplets, the white color pictures, these are all bismuth, okay, each one is a bismuth droplets. These bismuth droplets are actually formed by monotectic reaction in a complex aluminum silicon iron copper alloy. Okay. But fact that bismuth is miscible with aluminum, copper and iron and also probably silicon. So, bismuth comes out as a bismuth liquid, and bismuth it melts at 271 degrees Celsius temperature. Therefore, bismuth will remain as a liquid and solidify at the end as a droplets, and this is also signature of liquid phase immiscibility. So, let us now discuss the monotectic phase diagram in detail. Knowing this background informations, let us now discuss that. This is a more general monotectic phase diagram, and I have drawn it in a board. We will discuss in that, but before that let me just discuss with you the monotectic phase diagram. The most important signature is the monotectic reaction, and the reaction is like this: liquid L1 going to a solid phase alpha plus another liquid L2, and this happens at a temperature Tm. Tm is mentioned here. So, this is the monotectic point M on the phase diagram. But before that let me just explain you. Obviously, the liquid surface is this one. You can see here, this is like a isomorphous phase diagram, this part of the phase diagram from AMTA, this is like a isomorphous system. Then what happens? Then there is a change, you form a dome like structure, MKB dome like structure, and this is the immiscibility domain of the liquids. That means, if I take a liquid L whose composition lies between M and B, in fact, whose composition lies between A and B, will undergo the miscibility separations. That means, a liquid L will separate into two liquids L1 plus L2 at any temperature below Tc. Tc is the critical temperature. Okay, what is the meaning of that? Like suppose if I go back to mixture of kerosene and water, at room temperature they are immiscible. Now, if I heat it up, if I heat it up to about 40 to 50 degrees Celsius temperature, it will be a homogeneously mixed liquid. That is because if you heat it up, entropy of the system or entropic contribution of the system to the free energy increases. Why? Because G is nothing but H minus Ts. So, T into S is the entropic contribution to the free energy. If this fellow increases, then G can be lowered. Okay, even though H has positive value in these systems, but G can be lowered, and by doing that you can actually form a homogeneous liquid solutions at high temperature. And that is what happens at temperature higher than Tc. At temperature higher than Tc, what will happen? These two liquids L1 and L2, like kerosene and water mixture, will mix nicely and form a homogeneous liquid solutions. Or if I think other way, suppose if I take this homogeneous liquid at high temperature above Tc and cool it down through this dome, it will separate into two liquids with a composition given by M and B at a temperature Tm. Okay. So, these two liquids, one will have a composition given by this part of the curve Mk, other one will given the composition D part of the curve Kb at the temperature between Tm and Tc will form. Now, this liquid L1, once if you cool it down further below the Tm, this liquid L1 will undergo the monotectic reaction, which I have written here, L1 going to L plus L2, and that is what happens. So, this at this temperature, below this temperature, L1 will undergo this monotectic reaction leading to formation of alpha and L2. Okay. But any monotectic reaction, because you have a liquid, that it must be followed by a eutectic reaction or a peritectic reaction, and most generally it follows by eutectic reaction. That is what is shown here. At a lower temperature Te, much lower temperature than Tm actually, at temperature Te, this liquid L2, which is formed because of monotectic reaction, undergoes eutectic reaction forming alpha plus beta. But if you look at this monotectic reaction, eutectic reaction point here, that is at E, this eutectic reaction point is what? Iteration point is very close to the B end. So, therefore, the alpha page volume fraction will be very low, because alpha page is given by this arm, by the lever rule. This arm is very small. For the copper lead system, the eutectic point is 99.94% of lead. So, therefore, alpha copper is very small in the eutectic. It is basically a divorce type of eutectic in which beta is very large, alpha is very small. Okay. So, let us now discuss further. So, as you see here, we have got three important things happening here in this phase diagram, so which I list on the left side of this slide. First is that liquid which is at a high temperature, is a single phase liquid, undergoes the decomposition between two liquid L1 plus L2 here, L1 plus L2 you can see here L1 plus L2, and this is what happens at monotectic in between Tm and Tc, okay, Tc, this is what will happen between Tm and Tc. Now at Tm this one liquid L1 will undergo the monotectic reaction L2 plus alpha, this will happen at T equal to Tm, correct, and then from Tm to Te or above T what will happen, this liquid L2 will precipitate more alpha, nothing will happen, only precipitate more alpha, that is because the composition of the liquid is keep on increasing, so that is why there will be more alpha phase formations. So between this one L Tm to Te some more alpha phase will precipitate. Finally at T what will happen, at T the L2 will undergo the eutectic reaction forming alpha plus beta. That is exactly going to happen if you follow the alloy composition between A and B. Obviously any alloy composition beyond B, that is beyond B means from this point to this point, what will happen? Only thing can happen is formation of eutectic reaction. Those alloys will not undergo any kind of monotectic reactions or phase separations. So now let me just go to the board and discuss with you the aspects I told you now. So I have drawn the same phase diagram here on the board as you see here, okay, here this is the monotectic temperature, this is the melting temperature of A, this is the melting temperature of B, and this is the monotectic temperature Tm, and this is the point M, okay. So as you can see here, and this is the Tc, the critical temperature. As you can see here there are three sets of alloys we can see. One I told you the alloy composition from this to this one, these alloys are not of any importance for monotectic systems because these alloys will not undergo the monotectic reactions or any kind of phase separation. These alloys will undergo eutectic reaction. So therefore we will not discuss much on these alloys because they are not important to us. On the other hand, any alloy compositions, okay, between A and B will undergo monotectic reactions at Tm, but there are distinct classes between this. One is from this part to this part which will have liquid phase separation, that means L will separate into two phases, liquid phase separations, and any alloy between A and M will not undergo liquid phase separations, but it will have monotectic reactions, okay. Remember that this set of alloys will always undergo monotectic reaction, but liquid phase separation will not happen between A and M compositions, okay, no liquid phase separation will happen, okay, but both of them will undergo monotectic reactions. Now let us take an alloy compositions of this, suppose I draw a vertical line, suppose these alloy compositions, I will discuss about the solidification behavior. As you see here, if I take the alloy at this temperature, it is a fully 100% liquid L1, not L is above Tc, L1. So this liquid, if you cool it below the liquidus temperature given by this curve, this is more like a isomorphous phase diagram, this part of the phase diagram, okay, this liquid will form alpha phase in the liquid L1, okay, and so this is a two phase field alpha plus liquid. So this alpha phase will form like a dendritic manner, this will go like a dendrites, like a tree like structure into the liquid, and slowly the alpha phase composition will change by this solidus and liquid composition change by this liquid. Now at this temperature Tm, when the liquid composition will reach point M, just like eutectic reaction, same way liquid composition will reach M, this L1 will undergo the monotectic reaction, okay. So at temperature Tm, so above temperature Tm, alpha forms as a dendrite in L1, okay. Now at temperature T equal to Tm, there is a monotectic reaction, or you can say at temperature little bit lower than Tm, because it will not happen at the Tm, it will happen at lower than Tm, liquid L1 will undergo monotectic reaction leading to alpha plus L2. So, now we are going to form a new alpha, but this is not a new alpha, it is same as this, only difference is that this alpha has a little higher concentration of B than the alpha which is formed here. So, what will happen? Actually you will have alpha forming as a dendrite at temperature above Tm. Secondary alpha which is forming here, this is primary alpha because it is formed earlier. So, secondary alpha which will form here will be precipitating on these only. Okay. The same phase it will precipitate, only little bit composition difference will be there, but this will be same as the earlier alpha. This is also alpha, this is also alpha. This alpha is formed by without any reaction, by simply solidification from the L1, and this alpha is formed by monotectic reactions. Now, between Tm, so between Tm and Te in this temperature range, T less than Tm but greater than Te, correct, between this temperature range, what will happen? Nothing will happen except because the compositions at this point and at this points are different, more alpha will precipitate from L2, alpha precipitates from L2. Okay. The same it will also form on the existing alpha, nothing will happen, only at temperature, when the temperature will reach below Te, what will happen? This liquid whatever remain L2 at T, very small amount of liquid is left over, because you can see here almost all liquid will be consumed by monotectic reaction and the precipitation of alpha from the L2. The liquid will undergo eutectic reaction leading to formation of alpha plus beta. The point I am telling you this, because we are going to see the microstructure, point I am telling you this, that because the eutectic point is sitting very close to B range or B end, what will happen? Because of this, the beta will be very large quantity, alpha will be very small. That you can see, alpha is given by this arm divided total arm, and beta is given by this arm divided total arm, and alpha is given by this small arm, this one, this only, you can see here, divided total arm. So, alpha amount is very less. So, because of that it will form a divorce type of eutectic. Divorce means you will have alpha dendrites in which beta doublets will be present, nothing else in the microstructure. So, that is what will happen for any alloy composition sitting here. Now, if you take an alloy composition here, suppose this one, you will have an additional step other than this, that at temperature Tc, below temperature Tc, okay. So, for this alloy I am talking about it. So, this is P, this is A. So, these things has happened for, sorry, this is L, this is M, LM or no, it is really confused, M and N, L is transformed to liquid. So, this is for L. Now, M will have all these steps. In addition to that, before above Tm, or rather let us start above Tc, we will have full liquid L, and below Tc, okay, L will undergo liquid phase separation L1 plus L2. So, below Tc, the liquid L will then separate into two liquid phases L1 and L2, just like kerosene plus water. At high temperature they are a homogeneous liquid, at lower temperature they become two liquids, and then what will happen? Finally, this will liquid L1 will have composition given by this arm between M and K, and L2 will composition given by B and K. That is all will happen, right, nothing else. So, at then this will go back here. So, for the alloy we have added two more steps to 1, 2, 3. So, 3 plus 2, 5 different things will happen for the alloy N, okay. This is for the alloy N, sorry, all mistake will happen. This is for the alloy N, okay. The alloy N is this one that you see here. In addition to these 3 steps, there will be 2 more steps taking place. Now, question is this, let us suppose take a system, alloy system, and I want to tell you, because I am going to show you a lot of microstructure, copper and lead. And if I take an alloy composition for copper lead which lies like N, okay, N, what will happen? At below Tc, these two copper rich and lead rich liquid will separate. Now, as you know, copper has a density of 8.9 gram per cc, lead has a density of about 11.8 gram per cc. So, because of that, in a container if you take these two, this liquid, so lead will be sitting at the bottom and copper will be sitting at the top, because copper is lighter. Copper has density of 8.9 gram per cc, lead has a density of 11.8 gram per cc. So, because of that, there will be already a separation of this will take place, just like kerosene and water. Kerosene is lighter, so it sits top, water is heavy, it sits at the bottom. So, now, so this is suppose my L1 and this is suppose my L2, okay, L1 and L2. So, as you see here, L1, because it is sitting at the top, will undergo monotectic reactions at temperature T, okay, at temperature Tm, sorry, at temperature Tm, this will undergo monotectic reaction, okay. So, what will happen if I draw this picture correctly? So, this is T less than Tc, this is T less than Tm, so it will form alpha, this is alpha and this is L2 and this is L2, correct. So, you got clear. So, this L2 which is there will have almost same density as the bottom L2 and this will just go down, and because of that this dendrites which are form alpha, alpha is a copper rich or air rich solutions, alpha will float in the liquid. So, finally, this L2 will undergo eutectic reactions. So, finally, what will happen if I draw this picture, finally you have alpha dendrites and beta droplets into the microstructure will form, because eutectic reaction will lead to very small amount of beta, a very small amount of alpha, large amount of beta. So, therefore, you will not see it, and that is what you see in the microstructure. By seeing in the microstructure the like aluminum lead, what you are seeing? You are saying that these are the aluminum grains, large aluminum grains, and within that you have beta or lead droplets present, correct. These are the lead droplets I have drawn here present, and that is what exactly will happen in a real microstructure situations. Exactly this is what will happen. And now question is this, if you cool it slowly this is going to happen, but if you cool it very fast means suppose if you use a technique like rapid solidification, then because of fastness of cooling these two liquids will mix in the means they will form emulsion. What will happen? Because of that, this if I suppose I can draw it here and show you, if I cool it rapidly, this is slow cooling, if rapid cooling happens, rapid cooling will lead to a very interesting thing, it will lead to emulsion formation. What will emulsion formations? You will have lead droplets of liquid lead droplets, this is L2 and this is L1, this is known as emulsion. Instead of remaining two layers, separate layers, they will form like a droplets inside the liquid L1, and because of this droplet, because of this presence of droplets, the small droplets L2 will remain there, but L1 will again undergo monotectic reactions, form further L2 droplets, and finally you will have very fine droplets of beta phase in the alpha. So, that is what happens in rapid solidification of these monotectic alloys, and that is the reason I showed you the one of the emulsions. So, it is very clear by that by looking at this phase diagram that we can understand the phase formations or solidification of this alloy M, also this alloy N. The distinct difference between these two is that for this alloy there is no liquid phase separations, for this alloy there is a liquid phase separation like one at the bottom I have drawn, but for this alloy there is no liquid phase separation, only dendritic growth of alpha will happen and then further eutectic reaction will take place. But on the other hand here you can form droplets, and that is what I shown you in the microstructures. Okay, I hope it is clear to you, and you will be able to understand it by reading the books and by looking at the microstructure which I have shown you in the last class. Now, only thing which I need to do is that to complete the monotectic things is only to show you the free energy composition diagrams, which I will do in the next class, and in that class also I will talk about syntactic reactions, because syntactic is alloys are very less, and therefore we will not discuss in detail about the syntactic reactions. We will just I will show you how the reaction happens, and what are the ways microstructure can develop in these alloys. And subsequent to that we will go into the solid state reactions, mostly steels and cast irons. Okay.